Hi folks, in this video we're gonna go through bitwise shift operators. Bitwise operators are used to optimize an application if program is too slow. Maybe it's faster to use bitwise operators rather than normal arithmetic. Bitwise operators are applied to integer types, so remember that. Let's go through the left shift first. Let's imagine a 32-bit number. So that is a number represented by 32 bits. In a left shift operation, you're shifting all the bits to the left by some amount. Okay, and in doing so, you will lose the higher order bits, and 0 is padded to the right to compensate. Okay, let's consider this example. Okay, 3 left shifted by 1. Okay, 3 in binary is this. What I mean by hash 32 here is just my notation. It just means this number is actually a 32-bit number. Okay, what I mean by this dot 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 means 0 followed by 0 0 0 0 and so on, followed by 0 0 1 1. Okay, now have a look at this binary. If you shift all the bits to the left by 1, you can see that the leading bit here will be lost. It's shifted out. Okay, and then to compensate, you pad the right side with 0. Okay, so it becomes like this. Okay, and this over here is actually in decimal equal to 6. Okay, so this is like this operation over here is like 3 times 2 to the power of 1, which is 3 times 2, which is 6. Okay, that's the general pattern. What about a negative number? Yes, left shift can deal with negative numbers too, and it recognizes that in a negative number, sign is encoded by 2's complement. Okay, and what it means is the sign is encoded by the most significant bit, that is the leftmost bit. If it is 1, then the number is negative. If it is 0, number is positive. Okay, so have a look at this example over here. Okay, let's do -1 left shifted by 1. Here -1 is actually equal to 2 to the power of 32 minus 1. Okay, in general, if you encounter a 2's complement encoded negative number, so minus some number, that's actually equal to 2 to the power of 32 minus the number. Okay, so I was saying -1 is equal to 2 to the power of 32 minus 1, and that is actually equal to all the 32 bits filled by 1s. Okay, That's what it means. The 2 to the power of 32 minus 1. Okay. And if you shift this by 1 to the left, you can see that the leading 1 is lost, but it is all 1 anyway. It all 1s anyway in the subsequent digit. So what you're left with is this, right? Yep. And if you calculate, this is minus 2. Okay, so we got minus 1 and we got minus 2 out of it. Okay, why? Because same as the rule for the previous example. Okay, because if you got number either minus or positive, shifted by m, this is actually in general equal to number times 2 to the power of m. Okay, so here it's like minus 1 times 2, which is minus 2. Okay, so in general it says here, if you shift n by m to the left, it means n times 2 to the power of m. Okay, but here it also shows you if you got this, which is minus 2, we already know it's the result of the shift. How do you calculate the value minus 2? Taking into consideration that this leading bit here is reserved for sign. Okay, how do you know that this is minus 2? Let's go through it. There are two parts. First, you calculate the value of the leading bit, and then and this is 1, so this number over here, this is this bit over here, this number over here is actually a negative, and then you add on to that the rest of the digits. Okay, so there are two parts to it. Okay, so let's start with the leading bit. This is equal to minus 2 to the power of 31. Okay, and then the rest of the bits, this is equal to, remember what hash 31 means, it's just my notation that this bit over here, it's actually 31 bits long. Okay, and this one that you're gonna add on to is equal to this minus 1, right? Because because of here, this is like all 31 bits filled by 1 minus 1. Okay, and this is equal to 2 to the power of 31 minus 1, which is 2 to the power of 31 minus 2. Okay, so if you add those up, it becomes minus 2 to the power of 31 plus 2 to the power of 31 minus 2. Okay, and that equals to minus 2. That's how you do it. So just recapping, if you got a negative number encoded by 2's complement, the way to manually calculate the value of this 32-bit number is that first you recognize that this bit over here is for the sign, and if that is 1, then the value over here is negative. Okay, if the leading bit is 0, then the number is positive. So you first get this, and this is negative, and then you get the rest of the digits and you add those together. Okay, so it's like this bit over here minus this bit. And also, just lastly, if you have something like this, and then you shift it to the left by 1, then it becomes like this, right? So you can see that the left shift, even though it recognizes 2's complement, sometimes you will lose the sign. Okay, so this bit over here is actually starts with being negative, but now it's positive because the leading bit is 0 now. Okay, so the left shift operators are not necessarily sign conserving. Okay, let's do the right shift now. Okay, there are two types of right shifts: arithmetic shift and logical shift. Arithmetic shift deals with signs, and that means it deals with 32-bit numbers that are positive or negative. Logical shift only deals with positive numbers. Okay, let's start with arithmetic shift. Yeah, so this is a converse of the left shift. Let's say we got 32-bit number again, and in the right shift, you're shifting all the digits to right by a certain amount. So in doing so, you will lose the lower order bits by shifting, and you will pad the higher order bits to the left by either 0 or 1. Okay, and because arithmetic shift is sign operator, it will copy the sign bits so that the sign is preserved. Okay, in contrast, the logical shift, it will not conserve the sign. Okay, so let's do it. Let's do 35 right shifted by 2. Here it in this case is this is equivalent to 32 right shifted by 2, but this time logical shift. Okay, so these operators, one is arithmetic shift and another is logical shift. In this case, they are the same because it's dealing with positive numbers. The difference only appears if the number is negative. Okay. Okay. Binary in 35 is this. Okay. Now we're gonna shift all the bits to the right by 2 digits. Okay. So it becomes. Can you see here? Because it's all the bits are moving right. Because it's arithmetic, so it's sign conservative. This 0 is copied. Okay. So 0 is copied. Okay, and can you see here these two? are lost to the shifting. Okay, it's gone. So yeah, so it becomes like that. Okay, and decimal equivalent of this is actually a number 8. Okay, in here we can see that it's like 35 divided by 2 to the power of 2, which is 35 divided by 8. Sorry, 35 divided by 4. Okay, which is 8.75. But then you floor it, so it becomes 8. Okay, it ignores the remainder. Okay, alright, so that's how you calculate using a formula. Okay, so here in general, if you got x right shifted by y, it's actually equal to floor of x divided by 2 to the power of y. Okay, so here 35 divided by 4 becomes 8.75, and you floor it, so it becomes 8. Okay, what about a negative number? I told you that if the number is negative, then the two different types of right shift, they deal with it differently. Okay, so here in case of a positive number, if you are using the arithmetic shift as we are now doing it now, leading bits are copied. So if it fills the leading bits with 0, but in case of a negative number, it fills the leading bits with 1, so it keeps the sign. Okay, let's consider this example. Okay, minus 10 right shifted by 1. Okay, in this case we are doing arithmetic shift. Okay, so here this is not equivalent to the logical shift. They are not the same. Okay, so I explained above that the 32-bit number is if it's negative, it's stored using the 2's complement. Okay, anyway, the minus 10 is actually equal to 2 to the power of 32 minus 10. Okay, so in general, if you got a minus number that is encoded by 2's complement, it's equal to 32 to the power of 32 minus the number. Okay, okay, so minus 10 in binary is this, and we are shifting it to the right by 1. Okay, so it becomes can you see here, the leading bit has to be copied if it's shifted by 1 to the right. Okay, 1 is copied. Okay, yeah, so this is shifted by 1 to the right, so this bit is copied, this bit is lost. Okay, so here this is an error. Okay, that's an error because this should be like this. Okay, anyway, we can calculate this manually as we did before. Okay, so you first calculate the sign bit, each negative, then you add on to that the rest of the digits. Okay, so I will go through it now. So first thing, the sign bit is equal to this, right? Sorry, and this is actually equal to minus 2 to the power of 31. Okay, the rest is it will be right 0 1 1 0 1 1. Okay, so okay, so let's try it. So we got 0 1 1 1 1 1 until here 1. So 1 0 1 1, right? It's equal to this big number. Okay, so it becomes minus 2 to the power of 31 plus this number over here. Okay, and we're expecting it to be minus 5, because as you know, by formula, it means minus 10 divided by 2 to the power of 1, so it's minus 5. And let's do it. Yep, minus 5. Okay, and it says here, if you shift minus 1 right by any amount, the result is always minus 1. Okay, why? Let's see why. Okay, so minus 1 is equal to, by that formula, 2 to the power of 32 minus 1. And I told you this is equal to all the ones, all the bits filled by 1. Okay, and so if you visualize, if you right shift this by any amount, sorry, then you'll see that the leading bit is copied. All the high order bits leading bit is copied this much times, okay, by this amount. Alright, so doesn't matter how many times you shift, it will always stay as all the bits filled by 1, so it always stays minus 1. Okay, so we know that. Now we know that minus 1 right shifted, well, it has to be arithmetic shift. Okay, by any amount is actually minus 1. It stays minus 1. Okay, yeah, this one is a little bit tricky. Logical shift. I thought it would be interesting to logical shift a negative number. Okay, here it doesn't recognize 2's complement. Okay, just treats the binary as it is. Okay, so so minus 2 is this in 32-bit system. So yeah, so I guess so that's -2. Okay, so it is talking about when this is converted to binary. It has to use 2's complement, but then the post-processing of shifting, it does not recognize the leading bit as sign. Okay, that's the point. So yeah, so since the operator is on sign, the leading bit is not reserved for sign. Okay, so this so once we have converted -2 into binary, afterwards, well, beyond this point, we don't recognize sign bit. Okay, so if we got this is equal to every bit filled by 1 -1, right? Because of 0 over here. So that's equal to 2 to the power of 31 minus 2. Okay? And if you do that, you get this huge number. Sorry, 32. You get this huge number. Just a sec. Yeah, it's this is actually equal to 32. Yeah, anyway, so we got this huge number, and if you shift it by 1, then it becomes this. So this is equal to 2 to the power of 31 minus 2. So you can see here you get this number over here. So if you divide this big number by this, I'm sorry, you have to divide this big number here by 2, then it becomes this. Okay, thank you very much.